lecture for reliability engineering. I realized that we have some problems. I have some problem. Okay. So, in fact, I have some problem in providing messages into our chatting window, but I hope that the students do not have such problems. So, last time we talked about, in this course, last time we are currently talking about probability distributions, probability density functions, and probability distributions. And last time we talked about discrete probability distributions. And today we are going to talk about some continuous distributions. So, of course, last time we first I first gave you some introduction on the concept of a cumulative distribution function, which will be abbreviated as a CDF. And that CDF is the total, the CDF of a function at time t is given such that the probability that failure occurs prior to the time of interest t. So that is how we define cumulative distribution function. So if a time t is given, then we are going to calculate all the probabilities. We are going to sum up and in fact integrate all the probabilities that the failure, which is the time of failure, is currently denoted as capital T, and the probability that such failures occur prior to this time of interest. So that's cumulative distribution function. And probability density function, which is abbreviated as PDF, is given as the derivative of cumulative distribution function. So in other words, the CDF is given as the integration of probability density function. So probability is usually calculated. So I would say that, of course, PDF is defined later. So I would say that the CDF is usually defined as the integration starting from negative infinity to the time of interest t, and f t prime. So we just introduced a new variable instead of t to avoid confusion with the t in this place, dt prime. So cumulative distribution function is given as the integration of the probability density function. So if we want to calculate the probability that the failure or any event of interest occur between A and B, then in that case, the probability is calculated as the integration over A to B over the interval between A and B. So that is same as the cumulative distribution function. So CDF of B minus CDF of A. So this rule usually this rule generally applies to other to all continuous distributions. And with this knowledge in mind, we are going to review several continuous distributions. I guess you may be familiar with some of them, but for others, this would be the first time you would see what such probability distributions are. So the first example would be, so this would be the introductory part. And the first example would be normal distribution. Normal distribution is, you have seen many times while you talk about some statistical things. So normal distribution is widely used not only in engineering, but also in statistics. So it is also called as Gaussian distribution. And this is the form of normal distribution. And also you have seen the tabulated. So the probability is usually given in this form. And you have seen the table providing the integrated value. So in other words, the CDF, cumulative distribution function of normal distribution, and you could utilize it to calculate some probabilities, like the one given in the probabilities between T1 and T2. So last time I tried to, so today we are going to first start from normal distribution. So today I'm going to describe or explain these continuous distributions in more detail and try to kind of derive, not exactly mathematically derive, but derive such that you have some basic concept on these distributions. So, if we want to understand what normal distribution is, or how this probability distribution is derived, then we first need to know that we first need to understand some fact that, not this one. So integration from minus infinity to plus infinity and exponential function of minus x squared minus x squared dx. I think you have not seen this type of function many times. If we take the square of this, of course we are able to, by following several steps, we will be able to calculate this, and it will turn out that the final result would be pi. It takes some time. It is not that difficult, but well, why don't you just give a try? So instead of simply saying that the result is pi, So let me explain how this can be derived. So if we want to calculate, first if we want to calculate this, then because this we are currently calculating the square of the parenthesis, then this can be divided, this can be changed to this form. And we may simply change, instead of using x squared, if we change this to y squared and y, the result will be same. And this can be this will be same with x squared plus y squared. X squared plus y squared dx dy. And then what we need to do is to calculate. So in Cartesian coordinate system, it means all space, every points in xy plane. And if we change the coordinate system, the same thing can be changed to so instead of using Cartesian coordinate system, we are going to change this to polar coordinate system. So in that case, the r changes from 0 to infinity, and the angle theta will change from 0 to 2 pi. 2 pi. And in that case, x squared plus y squared is now changed to r squared. This will change to r squared, and dx dy actually changes to r dr d theta. And this will be same so if we take 2r dr equals dr squared, so we place 1 over 2 and instead of that 2, so what I'm saying is the 2r dr, this is equal to dr squared. So this is same with dr squared. So now with respect to r, it is integration from exponential minus t from 0 to infinity. That will be same with 1. So this is going to be same with 1 over 2 r, and what will remain is that so this is the integration result would be 1, and we still have 1 over 2. So the result is 2 pi, and 2 will cancel. The 2 will be cancelled with this half here. So the final result will be simply pi. So, so with this in mind, what we can say with this result, what we can say is that this integration result alone will be square root of pi. So maybe you will be able to see why 1 over square root is placed here. So what if we would like to, instead of exponential minus x squared, we are going to change this form to 1 over 2, and instead of x squared, and x minus mu, that's average value, x minus mu over sigma. So mu would be the mean value of the distribution, and sigma will be the standard distribution of the distribution. So in this case, this would be same if we insert 1 over 2 inside of this parenthesis, then it is going to be, so instead of this is going to be square root of 2 will be placed here. Square root of 2 will be placed here. So how can you calculate this? So instead, in this case, instead of the dx, so we are going to, instead of dx, let's take x minus mu. So in that case, we do not have, there is nothing changed here. Dx is simply same with the dx minus mu. And what if we would like to divide this with, square root of sigma. Of course, this would be different from dx minus mu. To make this equivalent, we need to multiply square root of 2 with the sigma, so that these can be cancelled out. So at this point, I would like to ask whether you are able to calculate the final result. So maybe let's think of, maybe you substitute all these parts into others like t. So it becomes like exponential minus t squared dt. So that will be same with this one. The result would be same with this one. So multiplied with 2, and that means this part alone it will be square root of pi. So this will be alone, this alone will be same with the square root of pi. In other words, it can be written as 2 pi sigma. Or if we want to avoid some confusion, then sigma, we may place a sigma in front of a square root of 2 pi. This will be very important because when we think about f, so now we are able to calculate. So at least from this one, what we can see is that one over 2 equals 1. And this would be very important property to be a probability distribution. So even if we insert this constant inside of integration, the result will not be changed. So this will be denoted as this would be the function for normal distribution. So in other words, normal distribution, if it is written as fx dx, then it is given in this form. So if we go back to our textbook, so the normal distribution is given as 1 over square root of 2 pi, and well, sigma should be take out of square root. This would be some typo. Exponential minus 1 over 2 and t minus mu over sigma and square root. So if we change this to, if we delete dx and change t instead of x, then the form of equation will be exactly the same. So this is how normal distribution can be, or normal distribution can be derived. So normal distribution, in this case, mu is going to be the mean value of the distribution, and sigma is the standard deviation of the distribution. So we have a special form of normal distribution, that is standard normal PDF. Standard normal distribution. So standard normal distribution is usually denoted as capital G. So if we use x, then x minus mu. So I'm going to take this part, and so x indicate the random variable, and so by transforming any normal distribution, so for any normal distribution, if we subtract the mean value and divide it with the standard deviation, then the distribution is now transformed into standard normal distribution. And as I already mentioned, you have a tabulated result for the CDF of standard normal distribution, so that we can utilize in calculating many statistical problems. So normal distribution, of course, is an important distribution that is widely used in statistics. And also, it becomes the basis for the distribution that we are going to study from now on. That is something called the log normal distribution. So normal distribution, well, so this is how normal distributions look like. Oh, if we so how such distributions can be utilized in our MATLAB. So mu would be the mean value. So let's put it as 0. Standard deviation, sigma, is given as 1. So now I provided the mean value and standard deviation that is the same with those of standard normal distribution. Of course, we may change that to draw a graph. So I'm going to set starting from -3, so with interval 0.001 and until x becomes 3. Y is given as normal distribution probability distribution function. X and mu would be mean value, sigma would be the standard deviation, and plot xy will give us the result. Okay. So this would be the plot of a standard normal distribution. So what if we change standard deviation? So currently this is the graph for 1. So give this command hold on. And what if we change the standard deviation as 0.5? Then this would be the graph for the standard deviation 0.5. What if this standard deviation is 1.5? Then this would be the result for 1.5 when standard deviation is 1.5. Of course, we can change the mu value. So if the mean value is 1, then we are going to have this form of, so the graph is actually shifted to the right-hand side by this amount 1, so the span of 1. This amount, the graph is actually shifted to the right-hand side. So this is a normal distribution, and I guess most students are quite familiar with this. The next thing that we are going to study is something called log normal distribution. Log normal distribution. So first, it is a positively defined random variable. That means it only takes positive values. It ranges from so this is why it ranges from only positive value ranges from bigger than 0, greater than 0, and it can extend to infinity. So it says to be log-normally distributed if its logarithm is normally distributed. So if this random variable, not itself, but if we take the take the logarithm of the random variable, and then after that it is normally distributed, then it is called as a log-normal distribution. And it says that this log-normal distribution has considerable applications in engineering. One major application is that so this is one example, when the result of multiplication of many independent random variables can be the random variable of interest. So here it defines y. So y is the random variable for log-normal distribution, and t is the random variable for normal distribution. So t is normally distributed, and if we take the exponential function, then y will be log-normally distributed. So with this relation, so log-normal distribution, the important characteristic of log-normal distribution is that, so here we assume that x is normally distributed. So when x is normally distributed with sigma x, mu x would be to be consistent with our textbook, let's write this as t, so that the result can be consistent with our textbook. So mu t would be the mean value is mu t, and its standard well, its mean value equals mu t, and standard deviation is sigma t. Then and y is log-normally distributed. Of course, because this is also a distribution, this y will have a mean value, which is denoted as mu y, and standard deviation, also sigma y. So previously, in the textbook, it is given that y equals, so y equals exponential of t, exponential of t. So this is the relation between random variables. So if we introduce so what is the same is that t will be same with log of y. So these are simply equivalent statement. So let's write it as let's write it in this way. So instead, this is the relation between random variables. So when we describe some functions, we are going to introduce this lowercase y and lowercase t. So y, small y, will be used to describe the function for random variable y. So t. So this from this relation, in fact, this variable t will have this relation. So if y is used to describe to be a specific value of this random variable capital Y, and t is used to describe a specific value of a random variable capital T. So anyway, it is going to, from this relation, it can be said that t will be same as log of y. So what it means is that if we take the derivative of t, so dt, so if we take the derivative of y, then it is going to be 1 over y. So the derivative of log y will be 1 over y. And dy will be placed here. So why do we need this relation? So from so this is normal distribution. This would be normal distribution. And if we want to derive the relation for y instead of t, then of course t will be same with the log of y. So the basic relation would be same, would be almost equal. Instead of y, we are going to place log of y. And instead of dt, we need to change this dt into y. So with this relation, dt is actually dt equals to 1 over y dy. And if we move this y to here, And then let me place y here. So this part is the form of log normal distribution. So it is now written as, so if this f, this is another function of f, and if this is the function for normal distribution, so I'm going to write it as f of normal, and this would be the function for log normal distribution. So log normal distribution has this form of equation. So let's go back to equation. So log normal distribution. Well, so this is still need to be fixed. So this square root only applies to 2n pi. And sigma t and y should be placed outside of square root. And one thing to be clear is that we started from here, the log normal distribution for t. So that means the mean value, this is the mean value for t, and also this is the standard deviation for t. This is the standard deviation for t. Also, this would be the standard deviation for t. So starting from here, so this should be sigma t. Also, this one should be sigma t. And also this one should be mu t. So in this form of log normal distribution, we utilize not the mean value and standard deviation of y. In the equation, we use the mean value and standard deviation of t. So so with this form, now it can be said that it is the same with the one given in this equation 2.66, except that this square root only applies to only 2 pi, and sigma t and y should be placed outside of square root. And also, it tells us that we can still use the table for standard normal distribution with this transformation. So to define this distribution, and also here, to define this distribution, we need not the mean value and the standard deviation of y. What we need is the mean value and standard deviation of t. Not the distribution itself, but the mean and standard deviation of the normal distribution. And mu t and sigma t, so in other words, mu t and sigma t can be given with these equations. So mu t is given. So this is mu t can be calculated by providing the mean value and standard deviation of y, and also sigma t, standard deviation of t can be calculated by providing the mean value and standard deviation of y. And also mu y and sigma y can be calculated by using the mean value and standard deviation of t. So how can we utilize that? So let's first okay. So let's draw several graphs for log normal distribution. So mu t is going to be 0, sigma t is going to be 1, and x is defined in this time 10 to the power minus from minus 6 to 1. So I kind of, because the log normal distribution is defined for non-zero values. So starting from 10 to the power minus 6, and then x ends at 10 to the power 1. That is actually 10. So x is sampled from 10 to the power minus 6 to 10. Y will be log normal PDF of x mu t and sigma t. And plot of xy will give us the log normal distribution. So let me slightly so maybe 10 was too. I'm going to slightly change to 0.5. 10 to the power 0.5 is equivalent to square root of 10. So instead of this, once again figure. So this is how a log normal distribution look like in linear scale, in XY linear scale graph. And if we change, so in our textbook, we also, there is another, when sigma t is 0.5, so if sigma t is 0.5, oh, well, let me try this one more time. And hold on, and 0.5. So this is the one, the graph for when sigma t equals 0.1. When sigma t is 0.1, then this is the result. So here, let me show you why this graph is called as a log normal distribution. So instead of plotting this as x to y, we may apply the log scale to x and let me change this to 1. So figure hold on. Let's try it once again. So maybe if we change this to -3 to 3, then it will be more evident. So if we change x into log scale, then the shape of graph now look like a normal distribution. So of course, when we use the linear scale for x, then the graph will look a little differently. But when we utilize, as you can see here, when we utilize the log scale for x, then the graph just to look like a normal distribution. So that is why it is called as log normal distribution. So we just covered normal distribution and log normal distribution. So next one would be exponential distribution. So exponential distribution, maybe students have seen and also seen many times, and then I guess students are quite familiar with this type of function, exponential distribution. So the next one is exponential distribution. So when the lambda, we introduce this parameter lambda, and this lambda is called as a failure rate. So, yeah. So it's probability distribution function ft would be lambda lambda and exponential minus lambda t. So this is probability probability density function. Then what about cumulative distribution function? Cumulative distribution function will be the integration usually from minus infinity to time t. Minus infinity to time t and ft dt. But if the t is defined as non-negative value, so if the failure rate is given as lambda and the time t is defined as non-negative real value, real number. So in that case, because t is not defined for the value less than 0, so the starting point can be given as 0. So we are going to integrate this, and the result would be lambda will be taken out because it is a constant. So lambda here, and exponential minus lambda t. But here, when we integrate this function, then this lambda will be cancelled out with this 1 over lambda that is produced from the integration of this function. So this will be same with 1 minus exponential minus lambda t. So when t equals 0, the result will be 1 when time is t. So maybe here, to prevent some confusion, we are going to introduce a new slightly different parameter here. So the cumulative distribution function for a exponential distribution is given as 1 minus exponential minus lambda t. So this is the probability density function. So this figure illustrates exponential distribution function. So maybe we can so in case of exponential distribution function, lambda is given. First, we are going to assume that lambda equals 1. So x is given as starting from 0 until it becomes 5. Y equals exponential function of, so L multiplied with exponential function of minus L multiplied with x. So this would be the function when lambda equals 1. Of course, once again. So when lambda equals 0.5, when lambda equals 2, that is how the exponential function when lambda equals 2 look like. And when lambda equals 0.5, That's the one that is the exponential function when lambda equals 0.5. So after that, so these are how exponential functions look like. And last time we learned about Poisson distribution. And what it says is the exponential function is closely associated with the Poisson distribution. Exponential function is closely associated and or related to the Poisson distribution. So why is that? So when we define t as the length of time until the arrival or event or occurrence. So we are going to t as a random variable as the length of time until the first event occurs or the first arrival occurs. Or when we talk about the failure of components, then the time until the first failure occurs. So if we want to calculate that, it is given as so if we would like to calculate the cumulative distribution function for this type of event, then the probability will be given as when t is defined as the length of time until the first arrival occurs. And the first event or the first arrival occurs prior to the time of event, to the time of interest. So if this is smaller than or equal to the time of interest, that means at the time of t, at time t, this event or this failure, this event already occurred at the time of t. And we would like to calculate the probability that this event occurs prior to this time t. And in fact, that is the definition of cumulative distribution function. So, how can you calculate this? So I wonder whether how many of you remember the equation for Poisson distribution. So anyway, Poisson distribution is the probability, in fact, the probability distribution when a specific number like k event occurs during the time t, when the failure rate or event occurrence rate is given as a lambda. So Poisson distribution provides us the probability distribution for a specific number of event occurrence during time t. So if we interpret the same probability with the terms used in Poisson distribution. That means at time t, at least one failure occurs if t indicates the time until the event occurs. So in terms of Poisson distribution, if x indicates the number of events occurred, then at least one event occurred. We do not say there is only one event, but it can be said that during the time t, more than one event occurred, equal to or greater than one event occurred. So if we calculate this probability, that will be same as the ft, the cumulative distribution function of exponential distribution. So cumulative distribution function for constant failure rate or event rate. So because the Poisson distribution is also a probability distribution, its sum is going to be, the sum of probabilities will be 1. So if we want to calculate this can be calculated as 1 minus I'm going to slightly fix the equation. So it is same with 1 minus probability that there is no such event occurred. So the probability that at least one event occurred is the same with the probability that 1 minus probability of no such event occurred. And this is because if we add this probability and this one, then the result will be 1. Because the probability, the sum of all the probabilities should be always 1. So this would be 1 minus, I wonder how many of you remember the Poisson distribution. So here, in the denominator, we need to, so in fact, the equation was that k factorial. K indicates the number of events occurred. And in this case, it must be 0 event. And in the parentheses, we are going to have, in the numerator, we are going to have lambda t. Which, in fact, this is the place for rho, the mean number of occurrence. And that is same with the lambda t here. Rho to the power k, and here k is 0, and exponential minus rho. And as I told you, rho will be same with lambda t. So 0 factorial. Factorial 0 is defined as 1. Lambda t to the power 0 will be same with 1. So this will be same with 1 minus exponential minus lambda t. That is equivalent. So this would be equivalent to the CDF of exponential function. So of course, most of the students I guess we're familiar with the normal distribution and exponential distribution, while it would be, to many students, it would be their first time encountering this log normal distribution. And from now on, we are going to have other continuous distributions or continuous other functions, other distributions that students might not be quite familiar with. So maybe at this point, this is already 4:12, so very close to 4:15. At this point, I would like to take a short break, like a 15-minute break. And after that, we are going to start at 4:30. And of course, as always, I would like to check the attendance of the students. So I would like to ask all of you to leave your name in the chatting window so that I can check your attendance. I'm going to start the second half of today's lecture. So in our first half of today's lecture, I introduced to you three continuous distributions: normal distribution, log normal distribution, and exponential distribution. And as we can see, exponential distribution is also closely related to Poisson distribution. So maybe I may add here. So if so exponential, we have observed that Poisson distribution is exponential distribution is closely associated with the Poisson distribution by the fact that its cumulative distribution function can be derived by Poisson distribution. With that, the number of events occurred at time until time t is bigger than, equal to, or greater than 1. So that means at least one event occurred during the time interval t. So that can be calculated with 1 minus the probability that no event occurred during the time t. And with that, we could derive the ft cumulative distribution function for exponential distribution by using Poisson distribution. So after these three distributions, the next one, so the third one was exponential distribution, and after that we have this Weibull distribution. So this Weibull distribution is widely used to represent the time to failure or life duration of components or system. So it is defined continuous random variable t, and t is always bigger than 0. So this random variable t represents the time to failure, that is the time until the failure of a component or system occurs. So in many cases, it is usually assumed that this time to failure follow exponential distribution. But in some cases, Weibull distribution is also widely used. And as we are going to see, Weibull distribution is a generalization of exponential distribution. In other words, a specific case of Weibull distribution now reduces to an exponential distribution. So Weibull distribution. So here we are going to introduce two parameters, scale parameter, scale parameter alpha, and another one shape parameter beta. And even though, so in our textbook, this PDF probability density function is given, but it would be helpful for you to understand the Weibull distribution by seeing the CDF probability, the cumulative distribution function of this distribution. So, in fact, the CDF So you should keep in mind that the CDF of exponential distribution is given as 1 minus exponential minus lambda t. And here CDF is defined, given as 1 minus exponential minus, instead of lambda t, this time we are going to, this is going to be as alpha. So alpha, this scale parameter, because it is called as a scale parameter, because as alpha increases, then the time span, actually, it has the effect, the equivalent effect of changing time span. What it means is that if alpha becomes 2, then it is same. So let's assume that alpha is increased from 1 to 2. Then when t becomes 2, so when alpha equals 2 and t equals 2, then the final result will be same with alpha equals 1 and t equals 1. So it actually changes the time scale. So it is why it is called as a scale parameter. So take a parenthesis and power of beta. So maybe you may understand when this Weibull distribution becomes equivalent to exponential distribution. That is, when beta equals 1, the function is now reduced to exponential distribution. Where lambda equals where alpha or lambda equals 1 over lambda, or alpha equals lambda equals 1 over alpha. So I would like to ask whether, so this is the CDF of a wave distribution. Of course, we should be able to derive PDF out of this. Of course, PDF is the derivative of CDF. So, first it has, if we take derivative, then first it is going to be minus and minus, so minus will disappear. So we are going to have first this. And then take the derivative for this. Would be, so beta so first we are going to have this exponential function minus, they will cancel each other, and simply we are going to have this exponential function. And then we need to take the derivative for this. So this would be going to be beta minus 1. And then if we take the derivative of this, then finally 1 over alpha should be also multiplied. 1 over alpha should be multiplied. So what we are going to have is so how many alphas do we have? Beta minus 1 plus 1. So we have alpha to the power beta and as a constant beta and t to the power beta minus 1 t to the power beta minus 1 and then this exponential part. So this is the probability density function for wave distribution that is given in equation 2.75. So next one would be gamma distribution. So go back to our textbook. So this is wave distribution. Maybe we may also try to draw this. So what about wave distribution? Wave distribution. So we may define A equals 1, B equals 1. So in this case, the distribution will be same with exponential distribution. So after that, y equals wave PDF XAB, and plot XY will give us the wave distribution the wave distribution for A equals 1, alpha equals 1, and beta equals 1. Alpha is a scale parameter, beta equals the shape parameter. So why? Let's see why it is called. Beta is called as a shape parameter. So hold on. What if beta equals 0.5? Okay. When beta equals 0.5 and when beta equals 4. So when beta equals 4, the shape of the distribution is somewhat different from those when beta equals 1 or less than 1. What about beta equals 2? Okay, when this is the case when beta equals 2. So this is why this the beta. So alpha is a scale parameter. It may change the scale in x-axis or t-axis, and beta changes the shape of wave distribution. So beta is called as a shape parameter. After that, we are going to move on to gamma distribution. So gamma distribution, so previously we have seen that wave distribution is a generalization of exponential distribution. In fact, gamma distribution is also another generalization of exponential distribution. So as an example, if Ti, the time Ti between successive failure of an event has an exponential distribution, so if all the T's have exponential distribution with the same lambda, then the capital T, the T of interest in gamma distribution is the sum of all the random variables Ti's. So so later we are going to see that so gamma distribution is basically a generalization of exponential distribution. So cumulative time to nth failure. That is this t is given t is given as the subscript, the first one plus the second one plus goes on and on plus some nth failure. So here we are going to have a shape parameter. So previously in wave distribution, beta was called as a shape parameter. But in case of gamma distribution, alpha is called as a shape parameter. And when alpha equals 1, that means we are going to have consider only one failure that follows the exponential distribution. Then it will be reduced to exponential distribution. And in this case, beta is called as scale parameter. So what it means is that, so now this time beta, so previously the exponential function took the form of t over alpha, and this is the place for the scale parameter. And this time in gamma distribution, because beta is a scale parameter, we are going to have exponential function with the form of exponential minus t over beta. So in fact, ft is given as okay, 1 over beta to the power alpha and a new parameter, a new function is introduced. So capital gamma is used, and gamma alpha, and of course this will be called as gamma function. Of course, I'm going to explain this later. And after that, t to the power, instead of beta minus 1, this time we are going to have exponential t alpha minus 1, and as I told you, instead of because beta is a scale parameter, beta will be placed under, I would say under the t. So then, so more specifically, if we go back to here, we told that we said that it is a else failure, but this is the place for alpha. So this gamma distribution is the function for the cumulative time to alpha failure. So to talk about that, we first need to explain what gamma function that is used here, what gamma function is. So gamma function is defined as the integration from 0 to infinity and x, not t, x to the power alpha minus 1 and exponential minus x. Exponential minus x. dx. This is the definition of a gamma function. So gamma alpha is defined like this. So how can you perform the integration? How can you perform this integration? So if we apply the integration by part, then what we are going to have is minus exponential minus x and x to the power alpha minus 1, integration from 0 to infinity. So minus and x alpha minus 1 exponential minus x, that is the result of integrating this part. And integration should be performed from 0 to infinity. And because of minus and minus And in fact, because of this minus, now it is now changed to plus when we perform integration by part. So it's time to differentiate this part, only x to the power alpha minus 1. So if we differentiate this, then it is going to be alpha minus 1 will be taken out, alpha minus 1, and it's going to be alpha minus 2. And here what you can realize is that when we insert 0, x becomes 0. When we insert infinity, the exponential minus x will approach 0. So therefore, this whole part is actually result in 0. So we are going to only have this part. And one more thing, if we compare this, the original definition, and this, what we can see it is equivalent to alpha minus 1, and the only change we can see is that alpha minus 1 is now changed to alpha minus 2. And it would be equivalent to alpha minus 1, gamma function for alpha minus 1. So with this, if we increase, so with this relation, gamma function of alpha is equals to alpha minus 1 gamma of alpha minus 1. In other words, this is very unique property of gamma function. So gamma plus 2, gamma of alpha plus 1 will be, if we increase the alpha by 1, then it is going to be the same with alpha of gamma alpha. Alpha of gamma alpha. What kind of function? So you may compare this as with factorial. So factorial has the property. So what about in case of a factorial, n factorial equals n multiplied with n minus 1 factorial. Or in this case, n plus 1 factorial equals n plus 1 and n factorial. So, or n plus 1 factorial equals n plus 1 and multiplied with n factorial. So what kind of function will have this type of property? Or at least what you can see is that, or when we think about n minus 1 factorial, that is n minus 1 multiplied with n minus 2 factorial. So, what it tells us is that when n is a positive integer, so to see what gamma function is, if you see this factorial function, n minus 1 factorial equals n minus 1, in this case itself, n minus 1 and alpha n minus 2 factorial. That is actually the function minus 1. So, and if, so the point is that when n is a positive integer, then gamma function of n equals n minus 1 factorial. So let's think about this. So gamma function of this would be same with n minus 1 and n minus 2 factorial. That will be same with n minus 1, n minus 1, and gamma function of n minus 1. So this is the equation that we could see here. So gamma function has very similar characteristic compared to factorial. But the point is that alpha, in this case, alpha does not need to be restricted to positive integer. It can be any real value. It does not need to be any positive integer like 1, 2, 3, and 4, as factorials does. So, this is a special case, of course. So this is how gamma function is defined. And with this gamma function, ft is defined with this gamma function. So if alpha is a positive integer, then this function can be replaced with n minus 1 factorial. And to understand why this function is derived for gamma distribution, maybe we need to understand how a Lagrangian distribution is derived. This is the probability of exactly k failures occur between t and t plus dt. So at time t, exactly between t and t plus dt, exactly case failure should occur. So how can we calculate the probability density function for this case? So it should be for case failure occur between t and t plus dt, then before time t, there must be k minus 1 failures. So k minus 1 failures need to be there. So how can we calculate the probability that k minus 1 failures occur for the time duration t when the failure rate or failure intensity is given as a constant value lambda? In that case, we need to apply Poisson distribution. So k minus 1. So k minus 1 failures must occur prior to time t. So the probability that k minus 1 failure occur for that time duration t would be, this is the place for lambda. So let me take, this was the so instead of 0, I'm going to place k minus 1. So instead of lambda t, k minus 1, exponential minus lambda t. This would be the probability that exactly k minus 1 failures occur prior to time t. And the probability that the kth failure occur between t and t plus dt would be, lambda would be the rate of failure, and dt will be the time interval. So this is the distribution when exactly case failure or k failures occur to time t until time, in fact, t plus dt, but because dt is such a small probability. So this is the probability density, then exactly case failure. So for this one to be a probability, we should multiply dt with ft. So if we rewrite this equation, then there would be k minus 1 factorial. And how many lambdas do we have? Lambda, we have k lambdas. So the number of lambda would be k. And we have t to the power k minus 1. So Lambda was already multiplied, and exponential minus lambda t. I'm going to move this exponential to here. So if we introduce so so previously I told you that when n is a positive integer, then n minus 1 factorial is equivalent to gamma function of n. So this one would be equivalent to, so k, because this is k minus 1 factorial, this will be same with gamma function of k. Gamma function of k. And we are going to define, instead of lambda, where, so I would like to say, where we are going to define beta so beta is defined as 1 over lambda, or lambda is defined, well, lambda is defined, so beta is defined as 1 over lambda. That means lambda is same with 1 over beta. So this one will be same with 1 over beta. Then this lambda is now moved to, instead of being in numerator, it is located in denominator. And now, if we was also move 1 over k minus 1, now maybe we may define alpha as k. Then, if alpha is k, and beta is 1 over lambda, then even k can be now rewritten as alpha. Now this Lagrangian distribution now has the same form of distribution with gamma distribution. But the difference between gamma distribution and Lagrangian distribution is that in this case, k is a positive integer. In case of a Lagrangian distribution, k is a positive integer, while in gamma distribution, alpha does not need to be a positive integer. Once again, k need to be a positive integer like 1, 2, 3, 4, 5, and 6, while in gamma distribution, alpha does not need to be a positive integer. It can be any real number. So that's the difference between gamma distribution and a Lagrangian distribution. But at least by introducing this Lagrange distribution, you will be you may be able to see the exactly same form of equation, and that will help you understand what or how this gamma distribution is derived. Also, gamma distribution has relation with Poisson distribution. When t, because when t is the time until case or k arrival, so it is closely related to gamma distribution. So the general form of equation is very similar to the one that we used in exponential distribution. So this time, so the ft, CDF is given as, because t is the time until k arrival comes. And that time t is smaller than the time of interest. So that means until this small t, there should be more than k arrivals. There must be, at the time of t, there must be at least k arrivals, and maybe more than that happened. So this probability, because some of the probabilities are 1, these probabilities will be same with probability that the number is smaller than k minus 1. So the probability that the number of arrival is equal to or greater than k is the same with the probability with same with the 1 minus probability that the number of arrival is less than or equal to k minus 1. So this would be 1 minus. So we need to add all of that. When x equals 0, so when x indicates the number of arrivals until in minus, it becomes k minus 1. Here is the place for Poisson distribution, x factorial, and once again lambda t to the power k minus 1, lambda t to the power x, in fact this time it is x minus 1, lambda t minus x exponential minus lambda t. Exponential minus lambda t. And this would be the cumulative distribution function for this gamma distribution. Of course, we will be able to derive the gamma distribution by differentiating this cumulative distribution. So by differentiating this, and if it goes on and on, you may be able to do it yourself. We will be able to arrive at the exactly same equation. So the difference is that, of course, here we use the k, factorial of k, t to the power k minus 1, exponential minus not lambda t. So because we already introduced here, we also need to change this to t over lambda. Oh, I'm sorry, t over beta, not lambda. So that when for a special case, so this is what you are going to learn later. So chi-squared is called as chi-square distribution. Is in fact a special case of gamma distribution. So you are going to learn chi-square distribution later. This is the case when beta equals 2 and alpha equals n over 2 when n is so when n is given as degrees of freedom, then when beta equals 2 and alpha is defined as the half of the degree of freedom, then that is called as chi-square distribution. So maybe later you are going to learn about this. So okay, very in a similar way, we will be able to draw these graphs ourselves by using MATLAB or other functions, other software tools. So when alpha equals 1 and beta equals 1, when alpha equals 1, it becomes an exponential distribution. And as alpha changes, when alpha equals 0.25, it still looks like a exponential distribution. When alpha becomes 3, bigger than 1, then the shape of distribution is somewhat different. So that is why alpha is called as the shape parameter, and beta actually changes the span of time. So beta is called as scale parameter. So next one is beta distribution. Beta distribution. So let's first see read some text. In our textbook. So beta distribution is useful for random variables that are distributed in a finite interval. So usually in this case, so just 1 is missing here. So in this case, t changes from 0 to 1. T is defined between 0 and 1. And alpha should be bigger than 1, bigger than 0, and beta should be equal to or greater than 0. And I already explained what gamma functions are. So in fact, this beta distribution is widely used. So maybe PDF cannot be given in a closed form. So as a special case, when alpha and beta equals 1, beta distribution reduces to standard uniform distribution. So from 0 to 1, the value of beta distribution simply maintains 1. It becomes a constant uniform distribution. So practically, this beta distribution is widely used as an auxiliary distribution in non-parametric classical statistical distribution estimations, and as well as a prior distribution in Bayesian statistical inference. So beta distribution is widely used. First, it is useful as a distribution when the random variables are confined in a finite interval. When random variables interval is clearly defined, confined, and it can be widely used in Bayesian statistical inference. And well, in less than 10 minutes, let's explain what beta distribution is. So, widely used as a prior distribution for Bayesian statistical inference. Ft, when alpha and beta are the parameters, this form of equation is that, let's see, gamma alpha. Okay, gamma alpha. Gamma alpha and gamma beta over gamma alpha plus beta. And then T alpha minus 1, 1 minus T beta minus 1. So this is the basic form of a beta distribution. So to understand that, if you understand probability, so probability of n1 minus 1, let's call it events. This is the event that we would like to see, well, with the event that we are expecting. So first, n minus 1 events in time 0 and u. So to avoid some confusion, so this one indicates the time interval between 0 and u. And one event in u and u plus du. And 2 minus 1 events in u v. So what you can see here is that how many events in total occurred. In total, we have n plus 1, n plus 1, so n minus 1 and 1 event, and another n2 minus 1. So n1 plus n2 minus 1 events occur in the time interval from 0, u, u, and u plus du, and v. So until the time interval 0 and v. So in total, we have n minus 1 plus we have n1 plus n2 minus 1 events in this time period of from 0 to v. So how can you calculate the probability density function for this? So FTDT, first we need to see n minus 1 events in u0 in the time duration u. So what we should apply is Poisson distribution. And because it is also the probability that in total, so first we are going to see that in total during the time between 0 and v, so we have a v time. The time interval is in total, the time interval is v. We are going to have n1 plus n2 minus 1 events. So the Poisson distribution, when you apply a Poisson distribution, then n1 plus n1 n2 minus 1 factorial lambda t to the power, so the time is lambda would be the rate and the time duration would be v. So this would be the rho to the power, this would be the number of occurrence, and multiplied with exponential minus lambda v. This would be the denominator. The numerator would be, so first there would be m minus 1 event between the time 0 and u, and we have n minus 1 event and 1 minus 1 events. The time duration would be this. And after that, there is one event between u and u plus du. So that means what we need is lambda du. During the time interval du, and lambda would be the occurrence rate. And next, this time, n2 minus 1 events between the time duration would be v minus u. So the time duration would be v minus u. So we are going to have n2 minus 1 events, and minus lambda v minus u. So it is already very close to 5:45. So this one can be easily in fact, this one can be easily simplified. So I'm sorry, this one should be also n minus 1 factorial. So n minus 1 factorial, n minus 2 factorial, and this one will be placed in the numerator. So all the exponential, u, exponential minus lambda v, exponential minus lambda u, and exponential minus lambda a, lambda multiplied with v minus u will disappear, cancel each other. And if we count the number of lambda, lambda n1 minus 1, n1, and lambda n2 minus 1. So u over v so if we count the v and u, then first this amount, and also lambda will cancel each other if we count the number of lambdas in the denominator and numerator. Lambdas will be all cancelled out. What will be remaining is the first u, the ratio between v and u, and if because we still have du here, so this du also will be divided by v, and what will be remaining would be, if we divide v, then this would be 1 minus u over v. So what will be remaining would be 1 minus u over v, and we have n2 minus 1 of them. Okay. So if we change u over v as time as t, so maybe I hope you recognize that if we change this as t, n minus 1, and this will be changed as dt, and this one will be also changed as t. So I'm going to change the order t here. And just one more. If we change n1 minus 1 as, where is that? Gamma over n1 minus 1 factorial as gamma over n1, and this one as gamma over n2, and this one as gamma over n1 plus n2. Then we have the function very close to the one that we can see here. If we simply change alpha and beta with n, if we change alpha 1 and n1 and n2 with alpha and beta, then this function will have a very similar form with the one that is shown in this equation. So it is still already. So if you find the mean and variance is given in the textbook, so this is the mean value, and this would be the variance of beta distribution. So today we covered many continuous distributions. So normal distribution, log normal distribution, and exponential distribution, wave distribution, and gamma distribution and beta distribution. And I tried to explain how they are derived. So this would be still already 4 minutes have passed for the expected end time of today's lecture. So this would be the end of today's lecture, and next week we are going to start to talk about joint and marginal distributions and some basic properties. Joint and marginal distributions and some basic properties of random variables. So I'm going to see you next Wednesday.